Hello, in the last two videos I told you how to multiply matrices, but I didn't formally define what the matrix product was. So I'm going to tell you just now for a few minutes a little bit more formal of a viewpoint on the subject, and you probably won't like it very much, but it's good for completeness. So I could call my first matrix A, and so I'm going to write this matrix in the following way. I don't want to tell you how many rows there are and how many columns there are because I want my formulas to work for any number of rows and any number of columns. So I'm going to write it like this, A11, A12, and then I'm going to put a dot, 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 and this means, well, there's more entries, but I'm not going to tell you how many. And so I'm going to go over to A1, N. So this is telling you there's 1, 2, and then you count over to some number n, which I haven't told you how big n is. There's that many columns in the matrix. And then I'm going to start the same thing over here with the second row, A21, A22, and this will go dot, dot, dot over to A2n. And let me extend my matrix enclosing parentheses here a little bit. And then I'm going to do the same thing with the columns here. I'm going to tell you, well, they go on, but I'm not going to tell you how far. I'm going to tell you they go down to some row m. So this is saying there are m rows. And then I'm going to have AM1, AM2. Remember what these mean. This means entry in the first row in the second column, for instance. This means entry in row number M in the second column, and so on. And this will go dot, dot, dot over to the last one here, row M, column N, and this goes dot, dot, dot down here, dot, dot, dot diagonally. So this is a general expression for an M by N matrix. Well, I can play the same game with another matrix B. And here I can label the entries with B's. B11, B12. Now, so far, this is numbered the same as what these are because it means the same thing. First row, first column, first row, second column, dot, dot, dot. And I'm going to go over to B1. Now, this is first row, but I want to say column number L. L. Why? Well, because I'm going to have here a general K by L matrix. And remember the second number there, the L in this case is telling you the number of columns. So that's what this is. B21, second row, first column, B22, second row, second column, dot, 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 B2L, dot, 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 down this way, B. Now I'm going to put row number K, why? Because it's a K by L matrix, K1, BK2, dot, 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 BKL. Dot, 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 down this way, dot, 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 this way. Only need 3 dots. So if I have two matrices like this, recall that, and I'm kind of running out of room, so recall that we need, to be able to multiply these together at all, we need to have K, or N equal to K. Remember, we talked about that last time. The second number for the first matrix, this is the number of columns, and that also tells you the size of a row. See, this counts 1, 2, up to N. There's N entries in that row. It's the size of a row. Had better be equal to the height of a column. That's this number here. Number of rows is the same as the height of a column. See, we're counting 1, 2, all the way up to K. Height of a column. Those two had better match up, or we're not going to be able to carry out our little scheme of matching each number in a row here to each number in a column here. If they do match up, then we can tell what any given entry of the matrix given by multiplying these together is. Now, so here's what the formula is going to be, I'm going to write AB, so this is the product matrix, and then I'm going to put a IJ here. So what does this mean? It means I multiply the matrices together, and then I look at the entry in the row number I, column number J of the product matrix, and I ask, what is that in terms of the entries in these matrices here? And it's given by this summation formula, and this is the part that you probably aren't going to necessarily like very much. So I'm going to write here, I'm just going to use a letter P for an index of summation. And P is going to go from 1 up to N. Now this N here is the same as that N there, which is the same as this N here. And notice it also has to be equal to the K. So I could just as well have written K here. And what it is it is the common size of a row in the first matrix or a column in the second matrix. So it's a sum, and then I'm going to take the entry A, I, P, B, P, J. Now notice the P here and the P here is the same. And the reason why is because you're taking the first entry of the first, well, whatever row you choose. I guess I'm taking row number I. So there's going to be some row number I in here in the first one. And then there's going to be some column number J here in the second matrix. And so I'm going to take that row number I, and I'm going to take for each entry, you know, the first entry, the second entry, entry number 3, entry number 4, entry number P, whatever P is, as P counts up, starting at 1 and counts all the way up to N. I'm going to match them up. The first entry of row J in this matrix with the first entry of column J in this matrix. The second entry of row I in this matrix with the second entry of column J in this matrix, and so on, and add them all up. And this is what the expression for that is. Now, I have limited room here because I didn't erase that stuff there. So let me erase all this, and then I'll rewrite that formula, and I'll show you with just one little example, kind of work backwards from the formula to show you that it's just a way of making formal what we have already done repeatedly with multiplying matrices. So what I just wrote was that the product formula ABIJ is the sum from some index P starting at 1 and going all the way up to N of AI times P, B, P times J. So here's an example. And so we're going to have, I'm going to write a matrix 3, 2, minus 1, 7, 8, 0. And then I'm going to write one that looks like, say this, 3, 1, 7, 2, 5, minus 4. So this is a 2 rows, 3 columns, 2 by 3. This is a 3 by 2. And so we know the middle numbers match up, so the product will exist, and the size will be a 2 by 2. We know that has to be the case, because that's the outside numbers, the 2 and the 2 here. Okay, now let's look at a particular entry. And I'm going to look at this entry here. I'm not going to look, I mean, I could look at the top left one, but just so it's not, just to be interesting, I'll look at the bottom left one instead. So let's look at this entry here. And we work out how that should come out. I'm going to erase these to get them out of the way. Well, the procedure we said before was you take the bottom row in the left column here in order to get the bottom left entry here. Now that's, so this here is entry. What does bottom left mean? It means the second row and the first column. So if this here is A and this here is B, what we're looking at here is AB 2, 1. That's what we want. Now what our formula says, if we take the formula here, what the formula should say is that AB 2, 1 equals, now watch what happens here. I have my sum, and the P, well, the P is still here for now. This P goes from 1 up to what? Well, remember what the sizes of these were. This was M by N, this was K by L. And remember, this N here was the same N as I had in the summation formula, because what was it telling me? Remember when I wrote before, and you can rewind if you want to, the columns counted over in A, the columns counted over to N, all the way over to N. That's how far they counted. So this would go up to N here, and that's just telling you how long is a row, how high is a column. That's what it's telling you. So this will go up to 3. P equals 1 to 3. Now the A, I, P, B, P, J, this entry A, this first one, the I, well, you know what the I is, it's 2, because it's the one we want, that's what we're asking for. We're asking for the one in the second row. So this will become a 2. Now the P stays there, because that's what we're summing over. And then the B, once again, the P stays there, because that's what we're summing over. But the J, we know what that is, because that's what we want. We want the one in the first column, so it's a 1 here. Now, when I write out the summation, what does the summation mean? It says, take each value of P, starting at 1 and counting up by 1s, to 2, to 3, to 4, to so on, as high as it goes. Here it only goes to 3, so it's just going from 1 to 2 to 3. Take each of those, write the expressions for each of those values of P, and then add them all up. So all this means is A2, the first one, P starts out at 1. That's what the index of summation says there. P starts out at 1. A2, 1, B, 1, 1, plus A2, now the P counts up to 2. A2, 2, B, 2, 1, plus A2, and now the P counts up to 3. B, 3, 1, and that's all. It's these terms. Now, what terms are those, if we go back to the matrices here? Well, the A21, what does 2, 1 say? It says second row, first column. So that's this entry here. So that's equals 7. B11, what does that say? It says first row, first column. That's this entry here. This is 3. Plus A22, what does that say? Second row, second column. That's the 8 here. B21, what does that say? Second row, what am I saying here? Second row, first column, 7 here. That's this one here. Now you see what's happening. The first entry is matching with the first. The second is matching with the second in this row, in this column, which is exactly what we did before. It's exactly what we want. It's completely familiar. A23, that's the 0. B31, that's the 5. And then these all add up, 21 plus 56 plus 0, so that's 77. Now that was just this entry here. And if we wanted to find the whole matrix product, we'd have to find all these others. But we don't care, we just wanted to illustrate this formula here. And that formula will tell you the entries of a matrix product for any sizes of matrices.